Hey everyone, today we're talking about Newton's third law. We'll start with a little warm-up. If you would, draw the free body diagram of a driver of this truck, so the highlighted in green. If he steps on the gas pedal and is speeding up while towing a trailer. All right, so a lot of times I'm going to start my free body diagram with the force of gravity. I know that one is always going to be straight down, and I know that most of our free body diagrams are going to have that force of gravity. The only way to get rid of weight would be to be really far away from any other object. So this object obviously has weight if it's on Earth. It's also not falling because of the contact with the ground. So we have a normal force that is up, and it's the same size as the weight, keeping it balanced or in equilibrium. I also know that the driver is stepping on the gas pedal, which would make the wheels spin, which is trying to make the car speed up. So I'm going to put a force of friction in this direction that allows the vehicle to speed up. And lastly, that would be exactly what the free body diagram would be if it was just the truck. But the truck also has to have a way of experiencing the inertia of the trailer, and that is with this string that connects the truck and the trailer. So there is a tension force in the direction of that string back towards the trailer. So that's how the truck is able to experience the inertia of the trailer. That's why it's a little bit more difficult for the truck to move forward, because it's pulling along this trailer. But I've drawn the force of friction larger than the force of tension, showing that this vehicle, while moving to the right, is also speeding up. Okay, so we've done Newton's first and second law. Newton's first law told us exactly what's going to happen if the forces are balanced. If we're in equilibrium, then there will be no acceleration, right? So that is the law of inertia. If the forces are balanced, an object at rest will stay at rest, an object in motion will stay in motion. And then Newton's second law told us exactly what would happen if the forces are unbalanced. So if we're not in equilibrium, if there is a net force, then there will be an acceleration that's proportional to that net force. So F net equals ma. Newton's third law, again, you may have heard a variety of different ways of saying Newton's third law, but you've probably heard this one: for every force, there's an equal and opposite reaction force, or for every action, there's an equal and opposite reaction. I like to add that little word force in there because we are talking about individual forces here. So for every force on one object, there's an equal and opposite reaction force back on another object. So all forces come in pairs. We can't have a force on an object without a return force back on the agent. For example, if I touch my finger to my nose, it's impossible for my finger to touch my nose without my nose also touching my finger. So that reaction force back onto the agent. So what I want to do when I consider third law pairs, if I were to draw a free body diagram of something simple like just standing on the floor. So if I'm just standing here on the floor, my free body diagram would just be my weight down, Fg, and my normal force up, that is equal in magnitude and opposite in direction. And in order to identify a third law pair, what I need to do is make sure that for every force, I identify the object and the agent. The object is who's feeling the force. So in this case, this is my free body diagram, so I am the object. I am feeling both the normal force and the force of gravity. Now, the trap here is, if Newton's third law says that every force has an equal and opposite reaction force, a lot of people tend to think that the normal force and the force of gravity are third law pairs. But if we identify the object and the agent, we'll recognize that these are not third law pairs, and actually third law pairs always appear on separate free body diagrams. So they're never going to appear on the same free body diagram. So if we take a look at the normal force, for example, I'm experiencing the normal force because of what agent? What object is pushing on me? And that would be the floor. So the agent of the normal force is the floor. So what would the third law pair to that normal force be? Well, if floor pushes up on me, it means that I am also pushing down on the floor. So the third law pair to that normal force is me pressing down on the floor. How about the force of gravity? What causes me to have weight? Well, weight is mass times gravitational acceleration. So, of course, because I have mass, that's going to help me have weight, but it's also due to this gravitational field. And what object is causing that gravitational field? Well, that would be the Earth. So the force of gravity, the agent, is Earth, as I'm being pulled towards the center of the Earth. So what would the third law pair to that be? If my mass is attracted to the center of the Earth, I would say that the center of the Earth is also attracted to my mass with equal and opposite force. So as much as the Earth is pulling down on me, I'm also pulling up on the Earth. Obviously, the Earth's mass is way bigger than mine, so it has a much larger effect on me. For example, if I were to jump off of a desk, I will accelerate towards the Earth instead of the Earth accelerating up towards me, but that has more to do with our different sized masses. We are experiencing equal gravitational force. I'm as much attracted to the Earth as the Earth is attracted to me, so that would be a third law pair. All right, and what third law pairs are going to do is they're going to allow us to simplify what I'll call systems, which would be multiple objects moving together with the same velocity and acceleration. So with that example we did in the warm-up, the truck that's pulling on the trailer, we could also do the free body diagram of the trailer, and it would be very similar. It would have a force of gravity down, it would have a normal force up, and it would have a tension to the right. And what I like to do here is I imagine that rope and how the trailer is experiencing that tension. Well, every fiber of the rope is pulling on the next fiber of the rope, and they're all pulling with equal and opposite forces. So we have this chain reaction of third law pairs. So I would say then that the tension on the truck pulling to the left is equal to the tension on the trailer pulling to the right. So we have here a third law pair. And then, of course, we had the weight of the truck and the normal force on the truck, okay? Now, just to be clear that these are not identical normal forces and not identical weights, I might do FG truck and FN truck just to add that extra subscript to show that these are not the same. I don't want to imply that these two normal forces are equal in magnitude or that these two weights are equal in magnitude, okay? But the idea of a third law pair that helps simplify these systems is that if I were to draw all the forces acting on all the objects in a system, and I do like to color code them, so what I'll do is I'll do black for any forces that are not in the direction of motion or not in what I'll call the line of motion. I know this truck and trailer are moving horizontally. So vertically, nothing exciting is happening. Vertically, we're in equilibrium. The normal forces and the weights are all canceling out, so I'll just do those in black. The weight of the trailer, the normal force on the trailer. And then we have this force of friction on the truck as the wheels are spinning. So I'm going to do that in green. Anything that is in the direction that these objects are moving, that's trying to advance the motion, I'll do in green. So we have there the force of friction. We also have the force of tension on the trailer is in the direction of motion, so I'll keep that in green as well. And then any forces that are against the motion, trying to impede the motion, I'll do those in red. And I have here the force of tension. And what I want to imagine doing now is if I were to just add all the forces on the entire system, it would look something like this. I have the force of friction in the direction of motion. I have a tension that is against the motion. And then I also have another tension on the trailer that is with the motion. So what I've done is I've summed all the forces in the line of motion. I would call that the net force, or the sum of forces, and that would be equal to MA. And I'm going to use big M here because this would be the mass of all the objects combined. Now, what you'll notice is any internal third law pair, so any third law pair that is inside of my system, meaning both of the objects in my system are experiencing that force, those are going to cancel out. So it allows me to simplify this entire scenario by instead of looking at the two objects separately, I can imagine drawing a big box around them and just calling them a large capital M. This is the mass of both objects. And I'll draw a third free body diagram. So I've got the individual objects and now also the free body diagram of the system, which would be the weight of the system, the normal force of the system, and just that force of friction that's making the system move. So my system's free body diagram, since I've drawn this big box around the truck and the trailer, I'm not going to consider those internal third law forces because I know that they cancel out. So it allows me to draw this simplified free body diagram, and I could very easily sum my forces or find the net force. And in this case, since normal and gravity are in equilibrium, the net force is just the force of friction, and that would be equal to mass times acceleration. I could then find the acceleration of the system by taking the force of friction divided by the total mass. Now, if the system has this acceleration, but in order to classify these objects as a system, they must all be moving at the same speed with the same acceleration, it allows me to apply that same acceleration to both the trailer and the truck. So I can use that simplified free body diagram of the system, find the acceleration, and then I can apply it to the individual objects. Okay? So we'll take a look at a couple examples here in a bit, but that is Newton's third law. Thanks for watching.